Start the recording. There you go. All right, so welcome everybody to the breakout session on programming environments landscape for the ASCR facilities. I'm David Bernholt from Oak Ridge National Laboratory. We're also going to hear from Scott Parker and Jack DeSlip from Argonne and NERSC, respectively. And what we would like to do in this session is to present the programming environment landscape, more emphasizing the commonalities across the three facilities than the differences, which I think, there's a lot of other sessions at the meeting and otherwise that are focused on individual pieces of the programming environment. And we're not trying to replace those. We just want to make sure people have the bigger picture of what's going to be available across facilities and what may be challenging across facilities. So with that, we're going to start hearing from Argonne.
All right, thanks, David. And like David said, this is really just a very, very brief intro to the Aurora programming environment, and a lot of this will be covered in more detail at other sessions. Next slide. So first off, I just wanted to start by introducing one API. One API is sort of a term or a label Intel has introduced in the last couple of years to sort of denote their software stack that runs across CPUs and GPUs and FPGAs. And the term's a little bit overloaded. One API is in its sort of purest form, industry specification for a programming environment that encompasses DPC++. Which I'll talk about a little bit more later on as being Intel's implementation of SYCL. A lot of library APIs like MKL, and then the underlying runtime Intel has called level 0. But more commonly, it's used more broadly to indicate their sort of software development environment for GPUs. And that encompasses all the things in the spec, plus things like Fortran, OpenMP, performance tools, and things like that. And this is something that Intel released, their initial version of their One API toolkit about 2 years ago, or a little, actually, sorry, about a little over a year ago. And there's some links here for anybody who wants to learn more about that of the One API components. Next slide. But in general, I think this software stack should be familiar to most people. It's sort of derivative of Intel's long-standing software environment with a few additions. So we have the OpenMP5 implementation for GPU offloading that will be available on Aurora and accessible through both Fortran and OpenMP. And then the DPC++, which is Intel's SYCL implementation, along with Python. And libraries, again, something that will be familiar to most folks. It is the Intel MKL math libraries, and then what number of their deep learning libraries for DNN and DAL, in addition to MPI. And then a lot of their familiar tools, Btune and Advisor and Inspector will be there. Next slide. So as far as programming models that will be supported on Aurora, as I mentioned, SYCL is a major one. We also have OpenMP. In addition, we have several that are coming from ECP. So we have Cocos and Raja. And then beyond that, OpenCL will be available. And then we're starting to look at the possibility of supporting HIP on Aurora. And so this is a very sort of preliminary effort with sort of an experimental implementation. So it's not something I would really recommend that people target as a primary programming model today. But if anybody's interested, we'd love to hear from you, because we are looking for people that would be interested in trying out the implementation that exists today. And in terms of what's not available, not surprisingly, CUDA itself is not available, as that's an NVIDIA product. And like I said, we're hoping to provide HIP eventually. And we won't be providing OpenACC. I think OpenMP will probably fill the role of OpenACC for most people on Aurora and possibly on other platforms going forward. Next slide. And this just briefly shows sort of possible porting paths to Aurora. I think mostly this is pretty self-explanatory. If you're using OpenMP or OpenACC, you probably want to stick with OpenMP. Cocos or Raja are pretty straightforward. You just use Cocos and Raja. I think the real, decision point comes from CUDA codes. And there, what we've seen is most people have been pretty successful utilizing DPC++. And that the port has actually not been too difficult and relatively easy to do. But like I said, for folks who are interested, there is this sort of experimental HIP path that can be explored. Next slide. And as I mentioned, in the tool space, Intel has an implementation of both vTune and their vTune and Advisor tools that support Intel GPUs today. The support is sort of ongoing and being implemented, so we expect more detailed support as time goes by. But we have been using them successfully today to understand the performance that we see on the Aurora test bed. So I think they're in reasonably good shape for most users to try out. Next slide. And as I mentioned, Intel has been working on their MKL math library and other libraries and adding support for Intel GPUs. So, in the MKL space, we see a lot of their, fundamental MKL components have been implemented and work with both DPC++ and C and Fortran OpenMP offload on the Intel GPU testbed platforms. And so these libraries, Intel's goal is to have them implemented optimized for every Intel platform, and GPUs are one of them. Next slide. And in addition to the math libraries, there will also be support for AI and analytics in the form of the 1DNN and 1DAL libraries. Next slide. Oh, and then I'll turn it over to Jack, unless do we want to do questions as we go, David, or wait till the end?
If there are any immediate questions, maybe folks can ask them in the chat, and we will try to address bigger questions towards the end.
Okay.
Okay, thanks. Yeah, so I'm Jack Deslip, kind of representing the NERSC arm of this presentation. And why don't we just go ahead and go to the next slide, David? So right now at NERSC, we have these two systems in production, and the one that a lot of you in ECP have been kind of getting on and putting like kind of testing your applications and your libraries, and the performance has been recently Perlmutter. And so what we have sort of in production at this point is the 1500 NVIDIA A100 nodes. So this is the NVIDIA GPU that is one generation past the Summit GPUs. Let's keep moving. And just kind of put this in perspective, so Perlmutter is a pre-exascale system. We think that you can maybe learn about your application performance, and a number of people I know are very interested in targeting performance portability, and Perlmutter kind of provides a system for you to do those sorts of studies. But I will say that we're also kind of already beginning to think about what's next. The NERSC 10 procurement is sort of kicking off or underway, and this is a system that we expect to be kind of our first exascale class system that would arrive in like the 2025 timeframe. So not much I can say about that yet, but it's sort of in flight. Okay, next slide. So Perlmutter, of course, as I kind of talked about a little bit on the previous slide, is here now. In particular, the GPU nodes are available for the community. So those can consist of one AMD Milan CPU and 4 NVIDIA A100 GPUs per node. The Milan is essentially the CPU that's sort of before the CPU and Frontier, whereas the A100s are of course the NVIDIA GPU that follows on to the Summit, the GPUs. A couple other interesting aspects is that the system is using Slingshot, and it has an all-flash file system, kind of the first of its kind in the world. So a number of the ECP applications have been running on the system and kind of measuring performance and learning things about their applications, use of both GPU technology, some of the Cray technology that will end up benefiting them for the 2 exascale systems. Next slide. So the take-home message I want to say kind of about the NERSC programming environment is that essentially everything that is available as a GPU or accelerator programming model is available on Perlmutter. I mean, that's sort of maybe one of the benefits of having a mature technology. So we've kind of taken a practical approach and made kind of all of those available to our user community. We kind of recognize that a number of applications had existing CUDA applications. We're willing to kind of meet them where they are. There's even some applications that are using CUDA Fortran. But one of the things that we are really as a center pushing for is programming models that are portable and productive in the sense that users could kind of count on them to work across different facilities within the DOE or within the HPC space, as well as give them some longevity, have a sense that it will work on upcoming systems if it works now. And so a lot of those programming models that we're really actively pushing include OpenMP, Cocos, Raja, and we have really put together an effort to make sure that HIP runs on the system, as well as SYCL and DPC++, which Scott just mentioned. So we have a contract with CodePlay to enable DPC++, essentially the one API programming model for A100s or A100 GPUs on the Perlmutter system. And then, of course, we're seeing a really big uptake in some of these data analysis programming models or environments or frameworks like TensorFlow and, of course, PyTorch and the like. So next slide. I think that one might have been my last. Yeah, I guess I wanted to highlight that we do have these partnerships to make sure that we have compatibility with Frontier and Aurora. And then next slide, David. So in addition to the HIP and DPC++ partnerships that I mentioned, we also have formed a NRE partnership with NVIDIA to make sure that OpenMP offloading, so OpenMP like 4.5, 5.x features are available within the NVIDIA HPC SDK. This is what used to be essentially called the PGI compiler stack. And this activity is kind of been wrapping up. They've delivered this product in their public releases. You can test it now. It's part of the production NVHPC SDK. And there's a few remaining issues. We continue to work with them, but we think that it's testable. And next slide. And this slide just highlights what I mentioned earlier, is that we also have this partnership with ALCF and CodePlay to make sure that SYCL DPC++ is optimized for Perlmutter, and in particular the Ampere A100 GPUs. And I believe that's it for me. Is that right, David? If you go to the next slide, I think it's over to you.
It is. Thank you very much. So I'm going to talk about Frontier's programming environment. Consists of several different components. There's two major vendors involved, Cray, or now HPE, and the Cray programming environment, and then the AMD ROCm programming environment. And of course, we're pulling in software from ECP and from other activities, some of which I'll touch on, and also the open source community in a broader sense. So in terms of compilers, we'll have C, C++, and Fortran from Cray and from AMD, as well as GCC. So we're going to have, the ISO standard languages. We will have OpenACC through GCC, OpenMP in all the compilers, HIP in two of the compilers, Cocos and Raja, that's just straight C++, so we'll have that everywhere. And for those interested, UPC. If you have CUDA code, our recommendation, or the most straightforward translation for our Frontier environment would be to take that over to HIP. There's some semi-automated translation tools available. If you're a CUDA Fortran user, you could write HIP kernels, which is a bigger transition, and call those from Fortran. We will have, of course, a variety of debuggers and correctness tools and performance tools. I should mention here that if you're a Summit user, everything I've been showing on the last slide and this one and the coming slides in green are also available on Summit already, so you can use a lot of this environment on Summit. And of course, we don't have quite everything on Spock, more of it on Crusher as that gets built up and released. So we'll have many of the tools you're used to from the community and from the vendors. We also have a wide range of libraries provided by the vendors, provided by ECP and others. And although I didn't include a slide on it, we will have most of the machine learning frameworks that you're familiar with integrated with the optimized libraries on the system. So right now we have Spock available. This is the previous generation hardware, and our test and development system for Frontier called Crusher, which many of you probably already have access to. This is the same hardware as Frontier. And so on the system, we've seen a lot of good progress so far. Both the OLCF Center for Accelerated Application Readiness applications and the ECP KPP1 and 2 applications are on Crusher and working on performance and seeing pretty good results. Frontier is currently in testing and stabilization. We're expecting acceptance in the first half of 2023, I think, or 2022, I'm sorry. Block there. And if you are working on these systems and find that you're having some problems and need some help with the programming environment, if you have a liaison from OLCF, please work with them. If you encounter an issue, please file a ticket with the OLCF. Otherwise, we won't know necessarily about it at all and won't be able to track it. There are Crusher office hours that will be starting up this month, and also a series of hackathons and training events. So please take advantage of those as well. And now we're going to start talking about a little more detail about some of the individual programming environments that may interest you. So I'm going to start talking about HIP and CUDA. And wow, that was annoying. So HIP was originated by AMD. It's been ported to NVIDIA, and there's also a port to Intel GPUs in progress. So this is, HIP is basically a light translation of CUDA and implements it in a somewhat generalized way. Actually, the NVIDIA implementation of CUDA of HIP calls CUDA immediately under the covers. So you're actually getting, you're going straight into CUDA in that sense. And so this is a fairly straightforward approach, I think, for most CUDA applications if they want to translate their codes. The recommendation, because you can't completely automate this translation, the recommendation is to do the HIP CUDA to HIP translation once and then treat the HIP as your primary source from then on. I know people may not necessarily like that, but that is a fairly straightforward way, and you're not really losing performance with the HIP layer. So as I said, we have solid support for AMD and NVIDIA GPUs, and work is in progress through the HIP LZ project in ECP, which is still a little bit experimental, but it's working fairly well as well. And there are also some other efforts coming out of AMD that may interest people who are making strong use of the HIP ecosystem. Next up is Scott to talk about SYCL and DPC++.
Thanks, David. Yeah, so SICL, as folks probably know, is one of Intel's sort of primary vendor-supported programming models for Aurora. It's actually been around for a number of years, but I think in most people's minds, it's still relatively newish. My guess is most people encountered it for the first time in the last 3-4 years. But it has been around since 2014. And the latest specification release was just last year called SICL 2020 that added a number of new features. So SICL is a C++ based abstraction layer that sits on top of standard C++17. And it's made by the same organization that developed OpenCL, Kronos. And they sort of built on what they learned from OpenCL to construct this sort of more C++ oriented programming model. And one of the main features is it allows for single source code development. So your CPU and GPU code can reside in the same source file. And SICL is really something that's very aligned with C++ and sticks as close as possible to the C++ standard. Next slide. And DBC++ is really just an implementation of SICL done by Intel. So you can sort of, sometimes people will use the terms DBC++ and SICL interchangeably. They're not quite identical. Intel has added a number of extensions for new features that they feel like that the folks would need for their GPUs. And in fact, a number of these their additions got added back into the SICL 2020 standard. So today, SICL 2020 and DPC++ are fairly closely aligned. Intel's DPC++ implementation is open source and available on GitHub. And it also supports a plugin interface that allows DPC++ to run on multiple devices. Now, I'll give you a little bit more on that in the next couple of slides. Next slide. And this is just talking a little bit about the changes that were done in the most recent 2020 specification. So they introduced several major features, including unified shared memory, reduction support, modern atomics, subgroups, and a number of other items. Next slide. And so there are today, a number of SICL implementations out there. For Aurora, we're using DPC++, but another major implementation that's available across multiple platforms is Compute CPP. In addition to that, there are several other implementations. The HIP SICL is one that I see mentioned frequently too, in addition to those. Next slide. And one of the, as Jack mentioned, one of the things that the facilities have invested in sort of jointly has been in increasing the portability of SICL. So there's been a sort of joint effort between ALCF and NERSC with CodePlay to enhance the support for SICL on NVIDIA GPUs, and also an effort between ALCF and OLCF and CodePlay to implement support for SICL on AMD GPUs. I think the effort with NERSC is sort of building on some existing work, and so that's I'd say maturing fairly nicely now. The work on AMD GPUs is still sort of in its earlier phases, though we do have some good early results. And just briefly, I wanted to show you some of those some benchmarks that show how portable SICL can be. And so this is really these aren't showing full apps, but these are showing either Babelstream benchmark or some mini apps, RSBench, DSlash, and Lulish. I won't read through all the details on this slide, but the gist of it is essentially that on the NVIDIA platforms, what we're seeing is SICL's producing in most cases performance that's the 80 to 90% what you see with CUDA. However, if you do look at the DSlash performance, you'll see that SICL is actually outperforming CUDA for that particular benchmark. On the AMD platforms, SICL is showing to be very competitive with HIP, and this is actually not too surprising. In most cases, it is performing identical, and with the Lulish benchmark, it's actually outperforming the HIP implementation. And one of the reasons we see sort of very comparable performance is it leverages a lot of the HIP tool chain in the LLVM compiler framework. So it's using a lot of the same things under the covers as HIP. So, I think we see some pretty early, good early indications that, SICL has some promise as a portable programming model, and it's not something that's just specific to Intel GPUs. I think, like I said, the NVIDIA one is implementation is it's a little bit more mature, but I think with further investment, I think this would be a potentially decent programming model for future AMD platforms. Next slide. And just a quick summary. So as I said, this is it's a relatively new-ish programming model based on C++ from the Kronos group. It is available on Aurora, and as Jack said, it's on Perlmutter. I think there's maybe limited experimental support planned for Frontier currently. And there are many implementations. Intel's DPC++ is a major one, but CodePlay is also a big provider of a SYCL compiler, and there's the other Tricycle, Hipcycle, and NeoCycle. And next slide. And if you want to know more about this, there's actually 2 more sessions coming up. One tomorrow at 10 a.m. Eastern, and then there's another session next week at the Community BOF Days. And with that, I will turn it over to Jack.
Okay, let's jump right ahead to the next slide. So I think the take-home message that I want to send about Cocos and Raja is that these are in somewhat of a similar spirit of DPC++, but they're not created by any particular vendor. They're something that kind of emerged from the DOE and NSA labs, and I think I'm probably not stretching too far when I say that these are probably likely the best portable programming choice for modern C++ programmers or C++ programmers who like to make use of modern C++ features. Both of these are expected to be supported on all of Perlmutter, Frontier, and Aurora with optimized backends, as well as having an OpenMP offload backend that kind of provides a fallback or like a existence proof for kind of full portability to future architectures that support OpenMP. Next slide. So real quick, just like how does Cocos address performance portability? So this is something that I think I stole for this talk last year from the Cocos developers themselves. So what they're really trying to achieve is something that allows application developers to be productive, portable, and performant. So it's basically a C++ library. It's not a new language or language extension, although I know that in particular, the Cocos team is really engaged with the C++ standards. And, I think when the C++ committee increases the capability of sort of standard parallels, and a lot of what is in Cocos could end up being adopted. So yeah, I probably won't go into too many more details here, but can we go to the next slide now? So real quick, I think it sometimes is helpful just to see how quickly and simple the syntax would be to do a simple kind of parallel loop. And so here you see a serial loop, an OpenMP loop, and the equivalent for Cocos is for Cocos syntax. And so you can see that it's pretty easy to jump into. Next. And in terms of both Cocos and Raja, here's kind of a summary of their current availability across different backends. So first you have the CUDA backend, and that's sort of where the first backend that Cocos really produced, as well as Raja. And so those are essentially feature complete, production ready. In terms of Cocos on top of AMD GPUs, particularly using HIP, this is also essentially feature complete at this point. Same with Raja. OpenMP Target, I think, is essentially feature complete. I don't believe the Raja team has any plan to implement something similar. And then, Cocos and Raja on top of SYCL, I think that this is kind of nearing feature completion. There's been a lot of work towards optimizing these for. I see Christian Trotz. Yeah, this is sort of maybe an arbitrary distinction between production ready and feature complete. And yeah, so I think SYCL there's been a lot of progress towards making a really performant version of Cocos and Raja for the Aurora system with a DPC++ backend. So using them on all three systems, you could do modulo Cocos on ALCF and OLCF. And maybe I was just getting a little cheeky here, but I think the best way to read about how to use Cocos at NERSC is to kind of Google NERSC Cocos. There's a number of docs on how to use it. Okay, yeah, thanks for chiming in, Christian.
All right, so we'll talk about LLVM now. So LLVM is really the dominant infrastructure for compilers now in HPC. It's used under the covers by AMD, HPE or Cray, Intel, NVIDIA, and a bunch of other vendors. You've probably heard of Flang, which is the LLVM Fortran front end. That's still very much under development. There's an ECP project on Flang. It's not yet ready for use. So anybody who's currently providing an LLVM-based Fortran implementation is probably using classic Flang, which is based on the PGI Fortran front end, which was open sourced some years back. But work continues on the new Flang to take that over and replace it. And so through ECP and through vendor contributions and other things, there are a lot of development. There's a lot of development work going into LLVM to support things that are of interest to our community. And so the upstream, the vendors are participating, contributing upstream as well. So what you have is a situation where LLVM upstream has releases, and then the vendors typically follow and do the integration and additional testing, putting in their own special features and things like that, and then they release their programming environment that includes the LLVM-based compiler. And so you then have access to several different versions of LLVM, probably depending on what you really need. And so for the most part, if you want the greatest safety and stability and support, you probably should prefer the vendors' compilers. They tend to have value-added features for their particular hardware. If you need something that's closer to the edge of development, look at LLVM main or look at the DOE fork of or DOE branch of LLVM that collects a bunch of contributions from the ECP community. At OLCF, we have regular builds going on of LLVM, and they're available on our different platforms. Unfortunately, these are not all unified, so pay careful attention. These are all different. Unfortunately, I'm hoping in the coming weeks to unify these. And my understanding is that both ALCF and NERSC plan to provide similar builds in the future. And then let me also spend a minute talking about GCC. So GCC is it's really the other widely used open source compiler suite. It's often the default compiler for most Linux distributions, and it's historically been available at a lot of HPC facilities, whether it's provided by the vendor or the facility. It's not as vibrant in terms of development contributions as LLVM community is these days, but ORNL since 2020 has been working with Siemens, used to be called Mentor Graphics, on some HPC related enhancements to GCC, which I think do interest this community. So things that we've already completed include OpenACC up through version 2.6 of the standard, and we've more recently added the kernels, support for the kernels pragma. We have solidified the OpenMP 4.5 implementation. We've got CUDA 11 support in there, and all this has been done initially supporting NVIDIA GPUs, and now we're working on taking all that to AMD GPU support. There are various reasons that this is lagging behind a little bit. Part of it is the hardware. Actually, Siemens is waiting on MI200 hardware. So initially, what they're working with right now is the MI100. That's the processor in Spock, for example. It's not Crusher or Frontier's processor yet. We're working on OpenMP 5.0 with a few exceptions. And we've done some work on Fortran interoperability. That actually has been completed. We have a few more things on the books. We want to take OpenACC through 2.7 for now. We're looking at OMPT and also the 5.1 and 5.2 features of OpenMP. And if you want to be able to take advantage of this, once again, at OLCF, we have regular builds available through what we call user-managed software. It's not available on Crusher yet because, as I said, that hardware is not supported. But sorry, there's an inconsistency there. We should have version 12 has just been released, and so we should have that on our platforms. And so, for the other platform, this should support Perlmutter well. Unfortunately, we're not aware of any work in GCC that's targeting Intel GPUs at the moment. One other thing that we should say about this is the work that we've contracted for focuses on basic implementation and getting that correct. The way it works with Siemens is that performance issues are treated like bugs and they're dealt with separately. So if we don't hear concerns about correctness or performance issues, we can't address them. Of course, we don't necessarily have the money to address every bug that we hear about, but we will do our best to prioritize based on the impacts to people. And as Siemens gets most of the OpenMP 5 implementation done, we're hoping to ramp up the emphasis on performance in this work. Now, Scott, to talk about OpenMP.
All right, thanks, David. Next slide. So I'm not going to talk too much about what OpenMP is. I assume most folks are somewhat familiar with it at this point. OpenMP is, it's on its current spec of 5.1, and I think the view is that provides a fairly robust framework for offloading code to the GPUs. And this goes back a while in OpenMP. I think their first offloading support was in OpenMP 4. OpenMP, is kind of, our view is that it does provide a potential path to developing performance portable applications today due to the support that's being provided across the multiple vendor implementations. However, while all the vendors are working to support OpenMP 5 in the current spec, there's a lot of variation in terms of what is supported today and what features they intend to support down the road, as they view some OpenMP features as inappropriate for GPUs and don't plan to implement those. So I think for folks that are using OpenMP, the real challenge is understanding what implementations are available where and what features are supported and sort of what dialect of OpenMP is spoken on the various platforms. Next slide. So this slide tries to capture the sort of available or known implementations of OpenMP with varying degrees of support across the various GPU platforms today. And not surprisingly, NVIDIA has sort of the most options. But AMD, as David mentioned, is also there's going to be a variety of implementations there with support for AMD GPUs on Frontier. Today, as far as Intel is concerned, there's really just one implementation, which is from Intel. However, they have a long history of working with and implementing OpenMP in their compilers, and I would say that they've made significant progress in providing support for the GPUs today. Next slide. And this is just capturing the implementations that are available or plan to be available on Aurora, Frontier, and Perlmutter. Jack can correct me if I'm wrong, but from looking at the NERSC documentation, it looks like they're currently recommending, primarily using the NVIDIA OpenMP implementation today on their platforms. Next slide. So the real, I think, trick to using OpenMP effectively today across these platforms, and in particular for writing portable code, is understanding what's supported where. And this slide and the next slide, which is a continuation of this table, are actually from last year's ECP annual meeting. There's an update to this in the works, and it will be presented at a session, I believe, next week. So this is really just a preview or a pitch for folks that are interested in this to attend that session. But David, if you can go to the next slide, as you'll see, there's a number of features that are supported on some platforms and not on all. And so this is really one of the things that for folks that are using OpenMP, they're going to either have to experiment or try to get good information from the implementers as to what is supported on the platforms that they want to use. Next slide.
Yeah, I just have to interject here that in many cases, so this is just a matter of time. It's not saying that these things won't be supported. It's just that they're not there yet.
Yeah, generally that's what the X's mean. In some cases they say not planned, but yeah, and there will be more information at the following two sessions shown on the next slide. So folks that really want to get the details, I'd recommend attending these two sessions to learn more.
And Jack.
Okay, let's go ahead and jump to the next slide. So, one of the things I wanted to point out is that Fortran is still heavily used. I feel like it's kind of like that guy in Monty Python who's saying like, not dead yet. And so this is actually, I probably should have gathered some newer data, but you can see that as recently as 2018, over 50% of NERSC users were still using Fortran. And I don't think it's changed a ton since then. I think we have seen an uptick in C++, but not a significant drop in Fortran. Can you go to the next slide? And the Fortran Standards Committee is actually really quite active. Fortran 2018 being the most recent release of the standard actually includes a number of pretty forward-looking kind of features. So one, of course, is co-arrays, and this is sort of commonly implemented using both distributed and shared memory, and could potentially be implemented on accelerators too. Another kind of forward-looking feature is the do concurrent. This is a way to express parallelism right in the language itself. That said, I think I would admit that many Fortran codes still highly utilize directives, OpenMP, OpenACC, or like what are called like the CUDA Fortran kernels or CUF kernels. And these include some of the biggest codes in the HPC workloads around the world. For example, like VASP and Quantum Espresso, for example. And one of the challenges here is that, as compilers are transitioning to LLVM, I think David and Scott talked about that. The Fortran is not quite as up to date in the LLVM space as C and, for example, the Clang front end. So ECP is contributing to the Flang project, what kind of used to be referred to as F18, and this is an official component of the LLVM of the LLVM project. Can we go to the next slide? Yeah, so this is a kind of an example of how these compilers are evolving in conjunction with that kind of push towards the new a new LLVM Fortran-based compiler. So this is an example of the NVIDIA compiler showing the benefits of potentially using standard Fortran, the do concurrent clause, to achieve what previously was being achieved with OpenACC, for example. Next slide. So Fortran at the facilities. So I believe that at the ALCF on Aurora, you'll be largely targeting Intel's Fortran IFX at this point. At NERSC, we're relying on largely the NVIDIA HPC SDK, what was formerly the PGI compiler, as well as GNU Fortran. And OLCF, you have a few choices here, including the AMD's sort of ROCm Fortran, as well as Cray and GNU Fortran. And then, of course, as Flang evolves, I believe Flang will be available at all three of these facilities over the course of the next couple of years. So next slide. I think that's what I just sort of said. Yeah, so Flang is progressing. The focus, I think, so far has been a lot on syntax parsing, like correctness, and creating a working compiler. And really, I think the focus will be shifting now towards OpenMP, the OpenMP implementation, performance, et cetera. And I think it'll be really exciting to watch Flang progress over the next few years.
All right, I think that's the end. So I'm going to stop sharing, and thank you, Scott and Jack, for those updates. And I think now we can try to attend to some of the questions that may have come up in the chat, and I'm going to scroll back up to the top. So Sayang asks about NERSC 10, and I know the answer to that. The answer is it hasn't been determined yet, right? You can't talk about it.
Right, yeah, the project is really just in its early days, and it will be a competitive procurement, but it hasn't progressed that far yet. So
Christian asks about your OpenMP NRE. Are you planning follow-ups to fill in the gaps? Have you identified gaps? That's for you, Jack.
Yeah, and my response there is that right now we have an ongoing support contract with NVIDIA where we're identifying some of the bugs and gaps that need to be fixed or filled. And so we are continuing to work on it with NVIDIA is the short answer.
All right, Tom has put a link to the Crusher office hours that I mentioned in the chat. Thank you, Tom. Christian says the Kuda Raja, okay, talking about Jack's table, and that was Jack's comment about production ready versus feature complete, I think. Let's see, what else? So people chatting Fortran. We have a question about Flang. Will Flang include do concurrent offload? So is there anybody here who can answer that? I don't know definitively. I think it would be certainly interesting, but I can't say that anybody's tasked with it right now.
Yeah, I don't know if Johannes is on, like Johannes Dofert. He would probably be the best person to ask.
Or Pat McCormick, if he happened to be here,
yeah.
Who leads the Flang project, in ECP at least. Graham notes that NVIDIA will support that.
I would probably go as far as to say probably, but I'm not 100% sure.
Yeah, it's logical. I just don't know of any specific commitment to it. Other questions or comments? All right, well, the slides are in the Confluence if you're interested, and probably you know how to reach the three of us and other people at our facilities if you have further questions or need assistance with anything. Oh, wait. Phil asks, what plans or hopes for accelerated C++ standard library implementations? So C++ folks, Christian, Graham, others, I can't see everybody who's here. Sure, go ahead, Christian.
So, I mean, we know from NVIDIA, right, that they have actual plans and hopes to do this, and we actually have some, working stuff right now, right? I mean, it relies on certain shortcuts, like for example, replacing all your allocations with unified memory allocations, but that is probably the furthest we are right now. I'm not sure that we have concrete plans from anybody else. I'm not aware of any concrete public plans from anybody else to do this. One of the problems is that the effort in the C++ standard to define how to do heterogeneous parallelism didn't make it into 23, as into the C++ 23 stuff. And so that probably delayed a bit, other vendors going off and doing things. So I don't know, we'll see. But other than NVIDIA, I don't think we have any concrete efforts right now.
Graham, any further comments from the ISA standard perspective? Maybe not.
So David, can I, just ask a question? This is more to the audience, and maybe one for future thought. I think it would be helpful for the facilities to get some feedback from the ECP community on, their interest in the portability of the programming models, right? For SYCL or for HIP, this is something we're investing in, on the assumption that this is maybe of use to people, right? I mean, I know in ECP, in many cases, projects have implementations for their code, both in SYCL and HIP and CUDA. And I think that, that works for them, but is that what they want to have 3 years from now, let's say? They want to maintain 3 branches or multiple branches of their codes for different platforms, or would they prefer to say have, just a HIP implementation that ran everywhere, or a SYCL implementation that ran anywhere, or are they fine with what they have today? I mean, that would be useful feedback for us and for ECP to understand, in terms of the investments made in supporting the programming models across the platforms.
Yeah, that's a very good question, Scott. So we would welcome feedback on that. And just as a supplement to that, let me add, I mentioned, Scott and I think both mentioned that we'll have SYCL experimentally on Frontier, Crusher and Frontier very shortly. And if there's anybody particularly interested in trying that out, please reach out to me. So Christian, if you're asking specifically about SYCL on AMD, right now we've got sort of about 50%. And the question is, how much further is there enough interest to take it further? I think now it looks like you're asking about the larger community and so broader adoption of SYCL. Maybe I'll let Scott speak to that if he wants to.
So my question is more like, how solid is the support gonna be, right, for like SYCL on AMD or HIP on Intel or whatever, right? How solid can we make that, and how solid is it gonna be in particular if it is not gonna be adopted outside of HPC, right? I mean, the SYCL compiler and the HIP compiler is gonna be used by the larger community, which is using that hardware, right? As the vendor compilers, but these other compilers, are they going to be used by people outside of our free facilities?
I mean, I think that's a good question. I mean, I don't know. I don't know the answer to that. I mean, I will, going back to your earlier question, I mean, I don't think there's an intrinsic limit on how robust these compilers could be. I mean, what we're seeing is the implementations are able to leverage a lot of things in LLVM and other, open source parts of the tool chain. And so they, can kind of, make use of a lot of that. And so that it's not a heavy lift necessarily, but of course, making anything robust in practice means having, a number of people using it, finding issues, reporting them, and then the resources to fix them. And so I think the question is really going to be, if there's interest in the community, I think, and people use them, I think they could be, as robust as anything else out there. If not, then yeah, they won't get the investment and they won't be that useful, or they won't be maintained. So I think that's one thing we want to understand is, what is the market, or what is the interest, across the community for these? If it's limited, then maybe, yeah, it doesn't make sense to make further investments, but, they certainly have the potential to be viable products, I believe.
Yeah, unfortunately, it's a bit of a chicken and egg, so it's challenging. I do see a question from Katie that I want to get to, since she took the time to type it in. I assume that's the same question you have your hand up about. Do you want to voice it, Katie? Go ahead.
Yeah, sure. I mean, I think, all the folks as part of the ECP project have had funding for years to prepare for this moment to be able to run a Frontier in Aurora. But of course, there's many people beyond that community. And so the question is, and I'm sure we're going to get that at NERSC, is, I've got a CUDA code. Nobody's given me money for postdocs or extra funding here. And I want to be able to run on both Frontier and Aurora. What's the fastest and easiest way I can do that and get a code that runs on both systems?
I mean, I would say as a practical matter today, what you would need to do is, do a translation from CUDA to SYCL and a translation from CUDA to HIP. And I think that's the fastest you can do right now, which is not, probably the answer most people would want to hear. There are some automated tools for facilitating that, but there's still going to be some work, and people are going to have to understand then multiple programming models. They're going to have to understand CUDA and the differences between CUDA and HIP, and then of course SYCL. We do have HIP, limited HIP support for Aurora. I can't say that that's going to work in its current form today, just because it's sort of at a proof of concept stage, an early implementation. But with further investment, that might provide another path, which would probably be a lot simpler for folks, because they'd only have one code branch and one programming model that they have to understand.
Yeah,
So,
I would agree with that.
I think it's an issue. I mean, I hope we can find a resolution to this and make life simpler for folks, both for porting and maintaining down the road, so that they don't have to manage multiple programming models. And of course,
what if it was Christian wants everybody to use Cocos?
And yeah, I mean, that's Cocos, Raja, OpenMP are all, I think, portable options today, right? It's just really just a question of the effort and whether people want to go that route, and a number of codes have. But we have quite a few codes that have both SYCL and HIP and CUDA implementations today. I mean, by my count, looking through the SYCL implementations we have for ST and AD projects, we have over 24, sort of SYCL implementations, and I'm sure all of those also have something else, right? Most likely a CUDA HIP implementation. So, we have a couple dozen codes out there that have embraced this sort of dual strategy and have chosen for various reasons not to do something else, at least for right now.
All right, we have just 1 minute, so I think it's time to thank everybody for their participation. Thanks to Jack and Scott for their contributions to the presentations. And as I said, if you want to reach out to us after the fact, you know where to find us. Thank you.
Thanks everybody for joining.